that allows even regular knuckleheads like me to write correct programs. But your code can only be as good as your spec, right? In some sense, all the work we do in Coq is just a proof that the code has the same bugs the spec does, right? And no more, which is a huge improvement over the state of the art. So anyways, here in this case, I can't really screw up, right? Because this is just helping me write down definitions. And if I get the definitions wrong, the proofs are going to catch it. Okay, so hopefully people have some idea. Yeah?
But you could also have an alternative bind that is the definition with the bug and use that and prove everything with respect to that, and you'd be fine. This is modeling an underlying programming language. You can reuse states wherever you want.
That's totally right. Yeah, so everybody catch that? So I might, there's a couple things. One thing is I might define it intentionally in a way that would seem odd and it would look like a bug to a reader, but I'm doing it for some other reason. The other thing is I might actually have myself done it on accident, but if everything works out and my spec is right, the final system is also still right. And this is an important point, right? It is different from other methodologies. Okay, so hopefully people are getting some feel for what's going on with monads if you haven't seen them before. Basically, we get to wrap stuff up and we get to carry context around with us. And here in a minute, we'll see this kind of shine. So we're going to have a NOP, which doesn't do anything, right? It just gives back TT in the monad. We're going to have send. So this is going to be handy. It's going to take a node and a message to send, and it's going to construct a packet and put that in there for us. We're going to be able to send output. We're going to be able to get the state, the current state, and also to set it. And then the last thing is that we're going to use Coq's notation mechanism, so it'll be a lot easier to write our handler code. One thing that might be helpful, I didn't mark this as an exercise, but just to get a feel for how much more pleasant this makes life, when you're extending the systems later this afternoon, try to do it without going through the handler monad. It's a lot less pleasant. Okay, so what have we done so far? We defined a bunch of types, and we defined some syntax and sort of small language for writing handlers, but we haven't actually built any systems yet. So let's do that next. We're going to build this really dead simple system just to get started. And this system is, not even actually distributed. So what we have here is actually a single node system. But it's going to allow us to see, some of the important things to think about when you first sit down to do proofs. Okay, so the first thing we're going to do is we're going to define the types of inputs. And this single node system is a sort of, stateful function, right? Clients can ask it for a fresh number, and it will give them a number that's never been seen before, right? So client messages look like get fresh. The response back to the client will be a natural number. The intention is that it's fresh. There's only one node in the system. We'll name it server, and its state's going to be a natural number. And because there's only one node, it doesn't make any sense to have messages. So we're going to go ahead and make that type empty, so that way later on in the semantics, when we get to the cases for message delivery, we can really easily get a contradiction out of it. Now here's another thing that maybe you haven't encountered yet, but it turns out that when you define a module in Coq, you can't actually satisfy the parameters using inductive types. So remember what we had earlier, right? We defined the type of modules that are the base system parameters. And they have to give us all these things. They have to give us the input type, the output type, blah, blah, blah. And now we're here doing it. We're defining inductive. But you'll notice that everything that's not a definition has a prime on it, right? And that's just to make Coq happy. So c'est la vie. Hopefully, I think I saw Eve earlier. Oh, yeah. Is 882 going to have module types instantiated with inductive?
I don't think so.
Okay. So this is a trick that will continue to have value, right? I'm giving you your money's worth. Okay, and then we just define some decidable equality for those parameters, and we are good to go. Okay, so now we have the base parameters. Now we want to define some handlers. And so what we're going to do is we're going to define system params, and we're going to instantiate that functor, right, that we wrote previously, handler monad. Right? So this is why we split things. So we can define those base types. We can plug those in through the handler monad. And now we're going to have all of that nice syntax that we were defining just on the previous buffer. Now for this system, it initially starts off where it hasn't given any numbers to any clients, so its state's going to be 0, right? So the first person that asks it for a fresh number is going to get 0 back, and that'll be fresh. And then when we get an input, right, which is going to be a request for a fresh number, we need to do something. So let's try to write that code here. Okay, so remember we define this functor. Functors are like functions from modules to modules. We define this functor, we define handler monad and this do notation and everything else. And now we want to use that to actually write a handler. So any thoughts on what we might need to do here? At a high level, what should happen?
Increment the current state.
Yeah. And so I want to update my state to be one more. Is there anything else I need to do?
That's the old one.
Yeah, exactly right. So let's try to write that. So suppose that we did it this way. So first I need to get my state out. So let's just suppose we did this. So I'm going to get my state. Now what I need to do, I want to set it, right, to the successor of that. So now it's one more. By the way, does anybody know how to make that not happen? It makes me so crazy, but not quite crazy enough to learn how to change it. Okay, so now we got the state, we set the state, and what do we need to do? We need to output the old value. Right?
You have to disable electric indentation.
Oh. But sometimes I like it, right?
Well, electric indent move.
I'll do it later, sorry.
Disable word and type electric indent. And it's a toggle.
Oh, nice. Okay, wait, hang on. Let's see. Oh, no. Hang on, if I hit tab.
Are you using tab?
Yeah. Well, anyway, sorry folks. Okay. Right. So high level, this looks like what this system ought to do, right? It should get its current state. It should bump it up one so that the next time it gets a request, it'll give out something fresh. It should tell the person who asked for it, like, here's a fresh number nobody's ever had before. You're welcome. Now, is this going to work when I advance the proof point? So here's a meta lesson. Whenever an instructor asks a question in that tone, the answer is no. Right? So what's going on here? Why didn't that work? Because that sure looks like code to me, right? I'll admit it. I write Python once in a while. And this is basically as good, right? So the term X has type state. What? What's type output? Oh, so that's actually one problem. I saw a hand. Did anybody else catch that? So you can't output a state. You have to output an output. Okay, I still think it's not going to work though. Okay. So what's going on here? Why doesn't this work?
The type handler monad TT is isomorphic to, but not actually equal to answer.
Right. So did everybody understand that? So what we have here, oh yeah, I have to repeat it. So what was claimed was that we're supposed to produce a handler, but here we've given a handler monad, in particular TT, unit handler monad. And there was a comment that's isomorphic, right? Because that unit doesn't contain any information, but we don't have any fancy pants axioms laying around to let us exploit that kind of stuff. So what's going on, right? So basically here what I've done is I've given a program. I've given something to handler monad. I need to actually run it. I need to make it happen. And that's why we had this do thing that I skipped over at first, right? So this do takes a handler monad and it gives you back a handler. So it takes a program and it's going to give you back something that will just take the state and sort of run it and give you the result back. So what we do is we just go like this. And now everything should work. Okay, great. So that's one handler down. So now we know how to handle inputs. Now the other thing we need to do is handle messages. So when somebody sends our node a message, what should we do? Well, in this case, there are no messages. So we're going to make this really simple and just, well, why did that work? Does that is, okay. If this wasn't a handler, that sure as heck is not a handler. Yeah.
Because you handle all the cases of the messages.
Yeah, exactly right. So everybody understand this? So for folks who are new, this might seem a little weird, right? One way to think about Coq is that you're constantly in this negotiation, right? And what we've done is, Coq told us, hey, I'm going to give you a node and a message, and you better give me back a handler. And what we did is said, oh yeah? Well, tell me which message that was. And for each way that you could have built that message, I'll give you back a handler. And there are no ways to build a message, so we're done, right? This is how, whenever you use contradiction or something, this is the stuff that's going on under the hood. And you can do it pretty easily by hand. Okay, so now remember earlier we were talking about bind. Oh, sorry, that's another point. So, one of the things that was really important to us when we built Verity was actually that we could verify implementations of distributed systems. So there's been a ton of, actually very cool, very interesting work on verifying models. This has, gone on for a long time. Basically, it's hard to reason about code that actually runs. But what I can do is I can sort of write down on paper, or maybe even in the computer, a simplified model of my system and reason about that. And the problem, of course, is that that has a large trusted computing base. Right? Any discrepancy between that model you check and the code that actually runs could violate all the correctness guarantees you provide. So the name of the game in verification has really always been about TCB reduction. The people who were doing it on paper were, in some sense, reducing the TCB. But with modern proof assistance, we have way more power to minimize the TCB. So our goal is to make this runnable so that the things we prove are actually the code we run. And just to give you a sense, we're not going to do it too much this week, because we really want to focus more on proofs. But this actually extracts to maybe if I do it one more time.
You have, try without that line.
Oh. I see. I think you're right. I think that I started this up with the wrong environment set. Okay, perfect. The version of the repo works with 8.8. Everything was built with 8.8. So, okay, great. So basically, right, this is OCaml code. You could have done it in Haskell or whatever. But this is all just regular code that you can actually run. We have all of our monad stuff in here, and here we have handle input, and it's going to do the bind and the get and the bind and the set, etc., etc., etc. Right? So the point is that you can actually run this. So what would you need in order to run this on a real network? So we define some types, what inputs and outputs look like, what messages looks like, and we define some handlers. These are functions that given a state and a message, or a state and an input, give you back a result, which is a new state, messages sent on the network, outputs to send to clients. If I actually wanted to take this Coq code and run it as a distributed system, what do I need to do?
Some network
I/O monads.
Sorry?
You need real monads for doing the I/O with the messaging connected to some OCaml functions which actually do that on the real network in the real world.
Yeah, exactly. I need something that sort of takes the output of the handlers and actually does something effective with them, right? In particular, I need like send, right? Like open socket. Read from standard input, write to standard output. So that code is called the shim, and it's also part of the TCB. And it's going to be a lot thinner with this approach than it is in sort of more traditional ways of trying to get distributed systems right. So the point here is just that we're actually defining things that in principle we can actually run. In real full Verity, we do that. Okay, great. So if you want to really run it, you go to shim. All you really need is input, output, and send. If you have those three functions, it's pretty easy to take the output of the handler and do the right thing with it. I guess you also want select to get message from the network. But we want to do proofs, right? So essentially what we want to do is we want to construct a model of the shim in Coq, and that's what semantics are. So let's move on to network semantics. Where is this? Whatever. Okay. So here, to define the semantics, we're going to have another functor, right? And what that's going to do is it's going to take a system. So it's going to take the set of all the definitions for the types. It's going to take the handlers. And it's going to give us back a description of the behavior of that system. OK, so the first thing we're going to do is just import those types so that they're handy. And then a lot of times in distributed systems, the specification you ultimately care about is what sort of behaviors of your system are externally visible, right? What can people outside in the rest of the world see your system do? Yes?
Why are you importing now and not the exclude export thing?
So here I just want access to the definitions. I don't want somebody who's using me to get those definitions from me. And this is where I mentioned earlier you kind of have to be careful with modules because you can't have duplicate definitions of the same name. So you kind of almost want it to be linear. So that's why I don't know if people have ever looked in the Coq documentation. Sorry, the question was, I should repeat it. The question is, why import? Right? A second ago I was doing include, and then I did export. What's the deal? So basically, I'm very carefully trying to make sure that everywhere I use this stuff, things are only defined once, but it's convenient to have the names I need when I need them. And Coq actually is pretty good about that, right? That's why there's include, import, and export. They give you these different flavors. So in this case, I just want to access the definitions. I don't want to actually, define, like have them as if I copied and pasted that code in here. I just want to use the names. Any other questions? Yes?
Why do you use a module and not a module type? I mean, wouldn't it better to just specify what the network is doing without having a concrete implementation?
So this is, I think people, so you guys have been following along with Quick Check. Oh, sorry. The question is, why use modules and module types? Isn't that like so 1970s standard ML style programming or something?
I think that's not the question. The question is, why is this a module and not a module type?
Oh, why is this a module?
Yeah, I asked if that would be a module type where you have just the abstract specifications of what the network does instead of the concrete. So you could basically verify against any abstract system which follows that specification instead of verifying it against one concrete implementation, which is this one.
So module types cannot contain definitions.
Yes, but you can basically specify how the network should behave, and then you would verify your system against any network which will follow that specifications. If you use a concrete model, you only verify it against that concrete implementation of a network, which is much weaker.
I'm not entirely sure I follow the details. So,
module types can contain definitions.
Are you sure?
Pretty sure.
I mean, I know better than to disagree with Andrew. So
why don't you just try it in Emacs instead?
That's a better idea. Maybe I was looking at something very old or wrong.
Maybe it only supports odd numbers in your own
Yeah. So, okay, all the more reason. So, you know, the first question I thought you asked was why modules instead of something hipper and cooler like type classes or canonical structure or something. I think you're asking something a lot more interesting, which is that you could do this more abstractly. Yes. And I think that maybe what you want is to have a system and be able to mix and match sort of the semantics that it runs on. Yeah, got it. Now I understand. And thanks for Adam for pointing out that I misinterpreted it. Great. So we're going to be able to run it on different network semantics because what we're going to do in here is define a bunch of different network semantics. That's one of the exercises. In actual Verity, it's all done with type classes, and so you can do that kind of ad hoc mixing and matching. Sort of as long as your system has handlers for the kinds of things that network needs handlers for to hook up with, you can mix and match all of it. Yeah.
In actual Verity, why do you use type classes instead of modules?
it was done for performance reasons initially.